Everyone, I'm going to complete section 4.7, data forwarding, data hazard, forwarding and stalling, and also discuss 4.8, branch hazard. This is the slide I shared last time. If you look at the top, register 11 is the destination register for subtract instruction, and register 11, unfortunately, is one of the source register in the subsequent instruction. So since register 11 is updated at the write back stage, you have to stop the pipeline at least 2 cycles in order to get the data, the updated value at the ID stage. So in order to resolve that issue, data forwarding or data feedback is one possible solution. If you look at the subtract instruction, although the data is actually updated in write back stage, the actual output, actual value of new value of register 11 is available at the end of execution stage. On the other hand, the AND instruction, although it tries to read the register 11 in ID stage, but you actually need that updated value of register 11 as long as it is available before the execution stage. That's fine. So this is basically idea behind the data forwarding. The data forwarding can happen, between the write back stage, execution stage, or memory to execution stage. For example, instruction in write back stage is producing a newer value of register 11, for example. And register 11 is one of the source register in the instruction in the execution stage. Then you have to get the feedback from write back stage to the execution stage. Similarly, there must be a feedback pass from memory stage to the execution stage in order to avoid the data, pipeline stall or pipeline the delay. So more systematically, we just draw the same data pass, feedback data pass from memory stage and write back stage to the execution stage. And there is a special additional unit at the bottom of execution stage, which is called a forwarding unit, is producing 2 control signal for the A and for the B. So for example, for the A is selecting one of 3 input candidates to the ALU source data number 1. One is coming from register file. The other one is feedback from write back stage. The last one is feedback from memory stage. So forward A control signal is selecting one of those 3 input candidate to the ALU source data 1, depending on the data conflict cases. So the forwarding unit, as you can see, is a 2 output signal. For the A and for the B are 2 output from forwarding unit, from the forwarding unit, and it's actually the 6 input, because the 6 input is actually the register numbers, and it is computing destination register in memory and write back stage is the same as the source register number in execute stage or not. So it is a 6 input, 2 output combinational circuit. So the question is the data hazard all resolved based on the data forwarding or data feedback? The answer is unfortunately no. So this is an example where the load word instruction is followed by addition instruction, and there is a data conflict on the register S5. So if you look at this first instruction load word, the newer value of register 5 is available after cycle 4. Because this is a load word instruction, you have to access the memory to get the newer value of register 5. Although it is written in cycle 5 in write back stage, the newer value is available after cycle 4. So addition instruction is trying to use it in execution stage. There must be at least one pipeline stop, pipeline stall, which is simply unavoidable. So in order to address that issue, there are 3 things. The first of all, we need to detect the case during the ID stage. when the load word instruction is in execution stage and there is a data conflict between the load word instruction and the another instruction in ID stage. So after it is detected, then you need to store the following instruction so that it repeats the ID stage again, because you need to stop the pipeline anyway, and also you need to stop the following instruction in the IF stage as well. So what I'm trying to say is that let us say in cycle number 1, the load word instruction is in execution stage. I'm looking at the figure at the top right corner, and I just denoted as instruction A, which is in fact load word instruction, and instruction B and C are in the IF stage and ID stage respectively. And in cycle, at the time, they identified there is some problem. There is some data conflict between the instruction A, load word instruction, and instruction B. So after it is detected, load word instruction simply move on to the memory stage. On the other hand, the following instruction, instruction B, is not able to move on because of the data conflict. Okay, you have to wait until the data is actually available. So the instruction B and correspondingly instruction C must stay in the current stage, which means that if you look at the cycle 1 and cycle 2, essentially the instruction B and C does not move ahead. They just stay the same stage. From the architecture's point of view, it doesn't really, it is relatively difficult to just to stay there doing nothing. So instead, what they are doing is just to repeat the ID stage again and IF stage and again. So that is kind of repeating the same stage one more time. And in cycle 3, the instruction A move on to the write back stage, and instruction B now move on to the execution stage, instruction C move on to the ID stage, and so on. So there are 3 things. The first of all, how do we detect it? And the second of all, how do we stall the instruction? How do we let those instructions B and C repeat in the same stage again? And so I numbered it 1 and 2. And the last one is the number 3 is in fact, if you look at the cycle 2, what does the execution stage is doing? And if you look at the cycle 3, what does the memory stage is doing? So that's something we need to also discuss, figure out. So I just demarked as a number 3. So for number 1, how to detect the hazard case? Well, first of all, load word instruction must be in the execution stage, and memory read control signal is one only for the load word instruction. So that makes sure that the instruction in the execution stage is a load word instruction. And then you need to see that the destination register in load word instruction is the same as the source register in ID stage. So that's the second line in the condition. And if that condition satisfies, then you need to stall the pipeline 1 cycle. And number 2, how do we let the instruction in B and C in IF and ID stage to repeat? Well, you can use the IF/ID write control signal and PC write control signal to prevent IF/ID pipeline register and program counter from changing, right? So if you remember, this is more like a flip-flop. When the rising edge of the clock, it will get the new value. If you deactivate the rising edge if you do not provide the rising edge of the clock, it will just continue to have the same value, as before. So that's a number 2. And number 3 is what is going to happen for the memory stage in cycle 3 and execution stage in cycle 2 in the previous slide. So it is more like passing the null signals to the following stage. So again, number 1, hazard detection unit is getting the mem read control signal from execution stage, and checking the register numbers, and if it is satisfy the condition, it will generate the number 2 IF, the ID write control signal, and PC write control signal, which essentially doing is that prevent program counter and IFID pipeline register values, getting updated. So which means that the instruction fetch stage and instruction decoder stage is just simply repeating the same instruction again. And number 3, when the hazard detection unit detecting the case, it will just pass the 0 control signal to the next stage, which is in fact 0 control signal including mem write is 0 and register write is 0, so which means that register is not getting updated, memory is not getting updated. So if you remember that every instruction is just supposed to either change the content of register, change the content of memory, or change the content of program counter. If any instruction doesn't do any of those things, it is actually doing nothing. So inserting the bubble is in fact, as long as you pass the 0 control signal, it is actually inserting the bubble or inserting no operation into the pipeline architecture. So, as long as you complete these things, then you are actually implementing the hazard detection and data hazard case. So section 4.8 is a branch hazard. So branch hazard is that, let us say, if you remember the branch instruction, the register 1, register 2, label, and in the IF stage, it is calculating, cycle number 1, it is calculating PC plus 4, as in the slide. And when the branch instruction moves to the execution stage in cycle 3, it is a computing branch target address. As you see, there is an adder in the execution stage. It is getting 16-bit offset, and it is getting the current program counter value, and it is added up to compute the target address. And when the branch instruction moves to the memory stage in cycle 4, it is actually the changing the set the program counter value to the target, so that it actually jumping to the target memory address. So this is what happened when there is a branch instruction in cycle number 1, calculating PC plus 4 in cycle number 3. It is a computing target address. Cycle number 4, it is now set the program counter to the correct target, the memory address. And then, the branch target can start in cycle 5. So if you look at the pipeline architecture, that actually means you have to stop the pipeline 3 cycles. So there must be 3 pipeline stalls, which is really really bad. So the point is that you need to stall the pipeline for every branch instruction, which is going to be really, really bad approach, because it really slow down the pipeline. It kind of wipe out all the advantages coming from pipeline architecture, in the first place. So alternative idea is to, let us just continue executing down the sequential instruction stream, assuming that the branch will not be taken. So this is more like a predict branch not taken. In other words, when there is an addition instruction, branch instruction, subtract instruction, or instruction in sequential order, you just assume that the BQ is not going to be taken. So you just continue to executing subtract instruction, or instruction, and so on. So if it turns out that the branch is not really taken, that's okay. Unfortunately, if the prediction is wrong and branch is actually taken, so in that case, the subtract instruction and or instruction, you already begin to executing those instructions, but you have to flush those unwanted instruction out of the pipeline. So we kind of kick out those instruction out of the branch pipeline architecture. So we'll discuss those issues in the next class. Thank you. So how can